resume.
Thank you. Before the break, we were looking at page 55 in your report, which set out the three classes of contaminants of concern and sediment. And I had meant to take you to page 53, where you've done the same with surface water. Now, let me just do that now quickly before we move to the next chapter. So page 53, there it's on the screen. Here again, in the same way for surface water, you have set out the classes of contaminants of particular concern. Is that right?
Yes, that's correct.
Put your mic on.
Yes, that's correct. In this this portion of the test, we identify 5 separate classes of contaminants, including conventional variables, such things as pH, the TSS, which stands for total suspended solids concentration, and turbidity. An indication of both of those latter two are indicators of the amount of suspended material in the water column. Nutrients, including nitrate, nitrite, and phosphorus, several major ions. There's a list of metals, and then phenols was identified as the 5th group of contaminants that were present at concentrations sufficient to pose potential risk to aquatic organisms in the Fraser River Basin.
Thank you. I'd like to move to the next part of your report, which is what you deal with in Chapter 5 of your report, and it's where you have gone through an evaluation of the contaminants of concern. So if you can just explain what was the intention with this part of your work as opposed to the previous section we just reviewed.
Yes. And so what we were trying to do here, in the first, in the Chapter 4, we tried to identify those substances that pose potential risk to aquatic organisms within the Fraser River Basin. In this evaluation, we're trying to focus our evaluation to identify those substances that pose potential risk to sockeye salmon specifically in the Fraser River Basin.
Okay. So everything else is falling out of the new sieve that you've got.
Yeah. Yeah, so to use our analogy of the sieve again, in this evaluation, what we do is we use less conservative assumptions for both exposure. We talk about exposure being exposure point concentrations, and we talk about effects. And in the first analysis, we talked about toxicity screening values. So in this evaluation, what we do is we increase the size of the pores in that sieve, so that we let drop out those things that are unlikely to be risk drivers for sockeye salmon. And the way that we do that is we apply these 2 separate types of assumptions that decrease the level of risk in the level of conservatism in the analysis. So first, on the effects side, rather than looking at conservative toxicity screening values that apply to any aquatic organisms that may be occurring within the Fraser River Basin, we use toxicity thresholds in this case that are specific to sockeye salmon, or just if we can't find sockeye salmon toxicity thresholds, we use toxicity thresholds for salmonid fishes, so animals that are very closely related to the animals that we're most concerned about. And instead of calling these benchmarks toxicity screening values, we call them toxicity reference values in this case, to distinguish them from the tools that we used in Chapter 4. And then the second thing that we do is, you'll recollect, we used exposure point concentrations to identify what kinds of concentrations of each of the contaminants of potential concern the sockeye could be exposed to. And we used, the measure there was the maximum concentration that was measured in each of those areas of interest. In this evaluation in Chapter 5, we've used a less conservative assumption. We've used the 95th percentile concentration rather than the maximum. And so by incorporating those 2 changes into this evaluation, it allows us to retain on the top of that screen those substances that we believe to be the primary risk drivers relative to potential effects on sockeye salmon in the Fraser, and the uncertain contaminants of concern, the things that we can't evaluate because of either limitations on data or limitations on the availability of toxicity thresholds.
All right, and if I can ask you, Mr. Lund, to put up table 5.18. This is T238, and this is a similar looking document to what we looked at previous to the break. But if I can ask you just to review that with us. So T238, yeah, 518. This is, again, shows the different life stages and the different contaminants of concern, and it shows it being measured with a 95% percentile exposure point concentration.
Yes, that's correct.
Okay. So what is this? And then we go on to 5.19, which is the next page, and 5.20, which is the following page. What do these?
Yeah, so in this analysis that we did for Chapter 5, which is a more detailed analysis of potential risks to sockeye salmon posed by contaminants in the Fraser River Basin, we've used three lines of evidence, or types of data, if you like, for evaluating potential risks to sockeye. We've used surface water chemistry data. Those results are presented in Table 5.18. We've used sediment chemistry data. Those results are reported, I believe, in 5.19. And we've used tissue chemistry data, fish tissue chemistry data. And those results are reported in 5.20. So if we go back to 5.18 for a moment, what this shows us that even when we implement these less conservative assumptions about both exposure and effects, we still see a number of contaminants that come through as posing potential risks, in this case specifically to sockeye salmon or salmonid fishes. And they include suspended sediments. It includes then also 5 separate metals and phenols in water. And as you can see, looking across the tables, those contaminants, at least a subset of them, are relevant for both for spawning and incubation period, for the rearing period, for smolt outmigration, and during adult upstream migration. So we have potential risk posed by one or more contaminants of concern through each of the 4 life history stages that we've looked at in this evaluation.
Okay, and then 5.19.
So in 5.19, once again, we've applied these less conservative assumptions in the evaluation. We've used the same data. The underlying data are exactly the same. The difference is that we've calculated the exposure point concentration, in this case, again, as the 95th percentile concentration of each of these contaminants, and we've applied a toxicity threshold that is less conservative than what we've used previously. And instead of using a threshold effects concentration, threshold effects light concentration, as we did in Chapter 4, what we've used is a probable effects concentration or a similar type of benchmark. Similar meaning the same narrative intent, same level of protection for aquatic organisms. And what we see when we do this evaluation is that a couple of the metals, iron and nickel, come through this assessment as posing potential risk to sockeye salmon that may be exposed to these contaminated sediments. And again, we talked about it a little bit before the break, and that is this evaluation of risk posed by contaminated sediments is strongly limited by the limitations that we have on the data that went into this process, and limitations associated with our understanding of how much sockeye salmon actually interact with contaminated sediments within the system. So those 2 uncertainties leave us in a place where we have a relatively higher level of uncertainty in the sediment assessment than we might have in perhaps some of the other assessments.
In 5.20, this table was actually one of the tables that was modified, and it shows up in your errata sheets. Is that right?
That's correct, yes.
Okay, so that, Mr. Lund, that's actually Exhibit 827, and the table has been reprinted within the errata at the very end. There it is. Okay, so what were you looking at here? This is a fish tissue sampling assessment, and that wasn't done for the earlier assessments in Chapter 4, right?
That's correct. So
what was being done here?
What we've done here is we've collated information available on the contaminants, bioaccumulative contaminants in fish tissues, specifically salmonid tissues. We've used sockeye and Thompson River Chinook tissues in this assessment. We looked at the data before we did that analysis and convinced ourselves that the data were similar enough between the species that it would not be unreasonable to combine the data to have a more robust data set. And for those who are following along but didn't have the errata, what we had in the original table was units for the metals that were milligrams per gram, and the correct units were micrograms per gram. So the analyses were conducted using the correct units, but the table itself showed the incorrect units when we printed it the first time. And so what this shows is that for roe, and particularly, we have some exceedances of the toxicity reference values for selenium. We have hazard quotients that exceed 1 for both at the Fraser River mouth and at the spawning grounds. And then for the sum of 2,378 tetrachlorodibenzodioxin toxic equivalents, that's some symbol TEQs in that final line of that column, it showed hazard quotients of greater than 1 for both at the Fraser River mouth and at the spawning grounds based on the data that we had available to us.
It identifies in the heading for this table that you have looked at contaminants of concern in Weaver and Adams, sockeye and Thompson Chinook salmon populations. Why did you only use those populations?
That was the data that we were able to locate to support this analysis.
In your view, is there adequate fish tissue sampling being done?
Not in my opinion, no. No, it's, if there is a lot more data on concentrations of bioaccumulative contaminants in sockeye salmon populations in the Fraser, we weren't able to access it. If what we had was the sum total of what was available, then I would say that is inadequate to characterize exposure and potential effects of bioaccumulative contaminants on sockeye salmon.
Is fish tissue sampling being done on a routine basis in any other areas of the province? Yes. Under a variety of different programs, there are fish tissue chemistry data being collected, for example, under pulp and paper. Pulp and paper liquid effluent regs. Each of the companies are required to collect fish for fish tissue chemical analysis. They're not sockeye salmon. These are typically, they may be sculpins, or they may be chub, or they may be some other forage fish species, but typically they're not salmon specifically. So while that kind of data is being conducted for other purposes, it doesn't provide information that is explicitly relevant for doing this kind of evaluation for sockeye or for other salmon. Sockeye salmon or salmonid species in the Fraser River, if that kind of a monitoring program was put into place?
Yeah, there's no technical barriers to collecting this kind of information.
Okay. And what does fish tissue sampling tell us that we can't understand by looking at water quality sampling or sediment sampling?
What's interesting about the tissue chemistry, fish tissue chemistry data, is it gives you a very clear idea of what the animals have accumulated in their tissues, of the bioaccumulative contaminants that they accumulate in their tissue over time. So rather than, when you look at water, concentrations of contaminants in water gives you an idea of what the potential exposure was. When you look at concentrations of contaminants in sediments, it provides an indication of what potential exposure was. When you actually measure the concentrations of mercury or dioxins or PCBs in the tissues of fish from the Fraser River, you know that they have been exposed to those contaminants. You know at what kind of levels they've been exposed, and it provides a basis for a comparison with toxicity thresholds that are explicitly developed for fish tissues. And so as a result of that, it provides a basis for estimating effects as well. So it's very, for certain classes of contaminants, is some of the most useful information that you can collect.
And is that information of any greater significance for migratory fish like sockeye salmon as opposed to a more local fish?
It's relevant for both. We certainly want to understand what's happening with resident fish species. That's very useful information they may be getting among the higher levels of exposure to these contaminants. But it's also relevant to fish that are migratory as well, because they can pick up they can be exposed to these contaminants and pick up their body burden as they migrate downstream through the Fraser River main stems, as they spend some time in the Fraser River estuary, as they're feeding out in the open ocean as well, when they're developing for the period of a couple of years during their open ocean residence, and they can pick up additional exposure on the way upstream. And so it's understanding what the levels are and what they are at various points of their life history provides a basis for understanding what those pathways are, what the sources are, what the pathways are, how they're picking it up, where they're picking it up, and where the concerns are relative to these classes of contaminants.
And what ultimately was your conclusion on the contaminants that you were able to assess, which are set out in relation to this chapter and set out on the tables 5.18, 19, and 20? What were your conclusions with respect to the impact on Fraser River sockeye?
What we concluded was that there are certain contaminants that accumulate in the tissues of Fraser River sockeye at levels that are sufficient to pose potential risks or to cause adverse effects on those animals.
Now, are there any uncertainties that should be identified in the toxicity assessment that you did?
Yes. So we went through the process of identifying sockeye salmon specific toxicity reference values to support this analysis. And for certain substances, we were able to identify toxicity thresholds that were explicitly relevant to sockeye salmon. In other cases, we identified toxicity thresholds that were relevant to salmonid fishes. As you take a step away from sockeye salmon and you look at salmonids as a whole, that increases your level of uncertainty a little bit. In some cases, we were unable to identify salmonid specific toxicity thresholds and ended up using fish specific toxicity thresholds. PCBs would have been an example of one of those. And then for a vast majority of the substances that were on our inventory, we couldn't identify toxicity thresholds at all that related to sockeye, salmonids, or fish. And so it left us with a large number of substances that carried through as uncertain contaminants of concern as we moved into through this the tail end of the Chapter 5 analysis.
Okay, and what about the exposure assessment? Were there uncertainties that we should highlight in that?
Yeah, we talked a little bit about the limitations on the available surface water chemistry data, the sediment chemistry data, the fish tissue chemistry data. All of these limitations affected our ability to estimate exposure point concentrations within individual areas of interest and for individual life stages within those areas of interest. And so the absence in many cases of data or limitations on those data creates a relatively high level of uncertainty in the results of this analysis. So to put that another way, you'll see a number of substances that are identified as those that occur at concentrations sufficient to adversely affect sockeye salmon. It would be incorrect to assume that there are no others that are present within the system at concentrations sufficient to adversely affect one or more life stages of sockeye salmon, because the data are so limited for so many suites of for so many contaminants, and limited on spatial and temporal basis as well, for those areas where sockeye salmon actually utilize habitats within the Fraser River Basin.
You'll remember earlier this morning we reviewed Table 8.1, which set out all the classes of contaminants and the various constituent chemicals under those contaminants. And it was a very long list, going on for 10 pages or so. The analysis that you did in chapters 4 and 5, which is sort of putting the contaminants through this sieve, were you able to identify with certainty all of those chemicals that show up on 8.1, Table 8.1?
No. The vast majority of those substances that are listed in Table 8.1, we were not able to evaluate using this systematic screening or detailed type of assessment that we've described in chapters 4 and 5.
Okay. And that's for the reasons that you've identified, some of the data gaps that you've already reviewed?
Correct.
Okay. All right, so nevertheless, the analysis that you did in chapters 4 and 5 and leading up to these tables, 5.18, 5.19, and 5.20, are the contaminants that were identified in that process important contaminants for us to be aware of vis-a-vis sockeye salmon?
I'm sorry, could you restate that question?
Although chapter 5, you were able to evaluate a more limited subset of all the potential contaminants, are those still important contaminants for us to consider with respect to Fraser River sockeye, even though it's a smaller group?
Yeah, it's a shorter list of substances. It's typically the conventionals, the metals, and a few hangers-on beyond that. Those are very important contaminants. And one thing I didn't mention, by the way, on data limitations was, it came up because I thought about metals just now, is virtually all of the monitoring data, and I won't say all, but virtually all the monitoring data that we collect on metals right now is on total metal concentrations. And that's typically because our Canadian water quality guidelines are based on total metal concentrations. But there are other measures of metal concentrations in water that give, or in sediments, that provide a better indicator of what is biologically available. I'm speaking specifically here in terms of dissolved concentrations of metals in water. If we wanted to do a very thorough assessment of the potential effects of metals on sockeye salmon in the Fraser River Basin, that's another thing, another data limitation that we would need to address is we would need to move from collecting these concentrations of total metals to something that is a better indicator of what is biologically available to those salmon as they're engaging in the various life history stages.
And that right now we don't have that easily available.
We have very, very little dissolved metal data available to us. We had some, but very little, and certainly not enough to do a proper characterization of what exposure was like.
Okay. Once you had done the evaluation of the potential contaminants of concern and then the evaluation of the ones that are set out in Chapter 5, did you do some analysis to determine whether there was a relationship between productivity and water quality once you had done the analysis?
Yes, we did. So we were left sort of with this level of dissatisfaction, having worked through this process, given all the limitations that we talked about on the data and our ability to interpret it. So what we thought we'd do is a different type of analysis that looked at really two things. One is the overall indication of water quality conditions, which we captured using a water quality index. It's a standard way of incorporating information on many contaminants. You know, we talked about, for example, the percent of contaminants that exceeded the thresholds in Chapter 4. There's other indicators that you may be interested in as well. Things like not just how many contaminants, but how frequently individual contaminants exceed a benchmark, and by what magnitude those exceedances occur. And so the Canadian Council of Ministers of Environment, the Environment has developed something called the Water Quality Index that incorporates information on all of those indicators of water quality conditions into a single metric called the Water Quality Index. And so we took all of the data we had, calculated water quality index values for each of the life stages and each of the areas of interest within the Fraser, and then plotted those against measures of productivity of each of those life stages, called Ricker residuals, which I understand this has been discussed previously in this setting.
So if I can ask you to turn to figure 5.2, and that's in the sections with the footer F, not T, so it's a new section of the report, F65. This is a table that shows what is described as an expected relationship between salmon productivity, Ricker residuals, and water quality index. So can you explain what this shows?
Yeah. So we talked about the water quality index as we. I'll try not to get this in your eye over there. It's an index that goes from 0 to 100. 100 is indicative of very good water quality. 0 is indicative of poor water quality. Ricker residuals, that's on the y-axis, running up like this. And a high Ricker residual indicates that you've got relatively good productivity, and a low Ricker residual indicates poor productivity. And so what you would expect to see when you plot these two variables, one against another, is if water quality, as measured using the variables that go into the water quality index, is a primary factor influencing the productivity of sockeye salmon in the Fraser River Basin, you would expect to see this type of relationship that goes from basically the origin of this graph on up to the right and to the top.
Okay. And then you did that analysis looking at different stocks in the system, is that right?
Yes, that's correct.
So those pages follow 5.2, the figures 5.3 and following, and those set out, I think that 5.3 is for the Fraser Basin as a whole, if I'm right, and then 5.4 goes through, or excuse me, 5.5 goes through individual stocks.
Yes, that's correct.
Okay, so this is each figure, it shows a different life stage, is that right?
Yes, so if we went to, for example, 5.3, a couple of pages back, you'll see an indication of water quality index versus Ricker residuals for 4 different life stages here. The first graph is for the spawning areas, and the second graph is for the rearing areas. The third is for out migration of the smolts, and the fourth graph is for upstream migration of the adults. And what this shows is when we pull together this overall figure 5.3, and if we go maybe back up to the top, what we see is that when we look at all of the data for all of the stocks, for the whole basin, all time periods, we see a very weak but insignificant relationship between water quality index and the Ricker residuals. So that suggests that there's very little relationship between the water quality index and productivity of sockeye salmon across the Fraser River Basin when one is looking at exposure that occurs in the spawning areas. As you sort of work your way down this plot, and we look at the second plot, we see a sort of a weak negative relationship. Again, that doesn't lead us to believe that water quality index is a good predictor of productivity of sockeye salmon in those areas that are being used for rearing by those sockeye in the Fraser River Basin. And similarly, when you look at the basin-wide data, there is, again, no relationship between the water quality index and the productivity of the sockeye salmon when all of the data are pulled together all temporally into one place. So now what we've tried to do is in figure 5.4, I'm sorry, We've split that data into pre-1990 data. Those are those solid circles that you see there. And the relationship is plotted as a solid line for the pre-1990 data. And you'll also see hollow circles. Those are the post-1990 data. And you'll see the relationship between the water quality index and the productivity is indicated by a dotted line in that case. And so what we see in both of these cases, when we break the data out temporally, we still don't see what we would expect to see is, we've seen the declines sort of between 1990 and present over the last 20 years. What we expected to see if water quality was as indicated by these the water quality index, is a primary factor influencing the productivity of Fraser River salmon. We would expect to see for one or more of these life stages that relationship that we saw in figure 5.2, where we had an increase in productivity with increasing water quality index. We didn't see that here. And so when you aggregate all the data across the whole basin, you don't see that kind of relationship for the variables that go into the water quality index. Keeping in mind, the calculation of this water quality index is limited by exactly the kind of limitations that we had in chapters 4 and 5. We had data for conventionals, metals, phenols, very little else beyond that.
All right, so there could be contaminants that you weren't able to assess that could have an impact that just would not show up at all on these plots.
You would not see them using this tool.
Right. And then the next tables or figures that follow actually try and do this analysis for individual stocks, some of the stocks. And if you turn to 5.5, you'll see this is for the pit, and what we see is very little data on this particular stock.
Correct.
And if you turn over to the 5.6, this is Harrison, again, very little data. So I take it one of the limitations that you had here was that the stocks you were looking at, even you didn't have sufficient data on all of them.
Correct.
Okay, so, and if we look at one that you do have a bit of data on, Weaver, which is 5.7, this shows a bit more of a relationship. Can you explain what you see, not in the early phases, but in the out migration and upstream migration phases, you have a bit more data?
Yeah. So if, for example, you look at the out migration route data for the Weaver stock, pre-1990 data, there appears to be a relatively a relationship that would be expected, an expected relationship between water quality index and productivity if water quality was a factor influencing the outcome. Influencing the abundance of salmon in that system, and that relationship is less strong for the post-1990 period. And what I would caution us as we look at this is that although the relationships in both cases explain some percentage of the data, the variability in the data, like up to 50% of the variability of the data for the pre-1990 period, that relationship is not statistically significant. And so it's it's most of the data are between the water quality index of say 30 and roughly 50. So we don't really have a broad range of water quality conditions within which to evaluate there. And so sometimes you see these kinds of relationships that are somewhat spurious as a result of having limitations on the data. They're not covering as wide a range of conditions as we would like, or there's just simply not enough data to develop those relationships fully.
I'd like to move now to Chapter 6, where you talk about endocrine disrupting chemicals and contaminants of emerging concern. And I just want to pick up on what you were just talking about here when we were looking at these figures, which is that there's a whole wide range of chemicals which you were not able to evaluate based on the data available. And if we turn to page 73, this begins a listing of a series of chemicals or contaminants that you were not able to evaluate. They begin on page 73 of your report.
Yes.
And then they follow through all of page 74 and over onto page 75. It's a pretty long list.
Yeah, and keeping in mind that these are typically classes of contaminants here, and what is in brackets are typically some examples of the kinds of contaminants. This is not going to be a comprehensive list of all the things that we couldn't evaluate, but it gives you a pretty good idea that there is a very long list of substances that we couldn't evaluate using the either the screening level ecological risk assessment type approach or the detailed ecological risk assessment type approach, which is what we tried to apply in chapters 4 and 5 respectively.
Endocrine disrupting chemicals have a specific discussion in your paper, and I just wondered if you could explain for the Commissioner what those chemicals are.
Yeah. So they are a group of contaminants that influence either the production or the release or the metabolism or the binding or the elimination of hormones in an organism. So these and the hormones are the chemical messengers that we use within the body to do such things as maintain homeostasis, to regulate reproduction, regulate the immune system, those kinds of things. So it's the endocrine system is extremely important in terms of the function that it plays for organisms. And these chemicals, the endocrine disruptors, are those substances that either mimic or in some other way adversely affect the functioning of those hormones in the body.
And when we look at Fraser River sockeye specifically, what are the concerns of these types of chemicals vis-a-vis Fraser or sockeye?
So the kinds of effects that we've seen in fish previously are things like altered reproduction in fish that have been exposed to these endocrine disruptors. We see things, particularly adverse effects on the immune system. We see changes in thyroid function. Thyroid regulates metabolism in fish. So we've seen those kinds of effects, and there's a lot of different sort of twists on reproductive effects. You know, be they changes in the organism's ability to produce eggs, or in some cases you see changes in the gender, in the apparent gender of the fish, so that the male fish exhibit characteristics of female fish, like they have things like vitellogenin in their tissues, elevated levels of that, which is an indicator of what you would expect to see in female fish when they're getting ready to produce eggs. And you see gonads that look very much female-like. And so this kind of gender bending is something that is typically associated with these endocrine disruptors.
And they are bioaccumulating as well?
Is some of the, at least some of the contaminants that are known to be endocrine disruptors also bioaccumulate, and that may be part of the way that they are exerting their action.
Right, and what is the significance of a bioaccumulating chemical?
Maybe if you ask me that question a slightly different way.
Please answer it.
A bioaccumulating contaminant is one that is present in the environment at oftentimes very low levels in water or in sediment. And what happens is that through the process of either uptake directly from water or ingestion of prey items that accumulate these substances in their tissues, these bioaccumulating contaminants become present in predators like salmon at elevated levels in their tissues. And they frequently become elevated depending on where you're looking, what areas of North America you're looking at or elsewhere in the world. They can become elevated to levels that are adversely affect their use by humans, but they can also or by aquatic-dependent wildlife. Things like osprey that tend to eat salmon or other fish species can be adversely affected by exposure to bioaccumulative contaminants in fish tissues. But also they can accumulate to levels that are sufficient to adversely affect those fish themselves. So those are sort of the three types of bioaccumulation that we're, types of effects that we're concerned about when we think about bioaccumulative contaminants.
Right, and what are the pathways by which these chemicals may enter sockeye? You mentioned those two, water and prey. Is there other pathways that we should be aware of?
Yeah, water and prey are probably the two most important pathways. We can't categorically rule out direct exposure to sediments. I think it's a minor pathway because of where the salmon are incubating and where they're typically rearing in the nursery lakes, and they're utilizing primarily planktonic organisms as their prey species. So I think that's a minor pathway. So very likely direct exposure to water and ingestion of contaminated food represent the two primary exposure pathways for most of bioaccumulative contaminants.
And has there been sufficient research directed to understanding fates and pathways of these chemicals?
There has been some research done that helps us to understand sources and releases, and importantly, how these contaminants are transported within aquatic systems once they're released, and then how they're transformed, what their fate is, how they either become associated with the water column, or how they become associated with sediments, or how they become associated with biological tissues that can then be consumed and get this biomagnification effect of the food web. So that kind of information exists for a subset of these contaminants that are on this long list that starts on page 73. And it exists for a subset of the organisms that we care about in the receiving water environment. I would say for most of these contaminants, so the information needed to fully understand what the exposure pathways are and what the fate are for salmonids specifically are not well studied. And if they are, I haven't seen that information.
What are the point sources of these kinds of contaminants that are of the biggest concern vis-a-vis Fraser River sockeye on the Fraser system?
We think about the list. So I've identified two types of lists here. One is goes under the umbrella of endocrine disruptors, and the other is contaminants of emerging concern. And this list, starting in page 73, covers both of those groups of contaminants. Let's start with the endocrine disruptors first. Mm-hmm. So sort of the key sources of those in the Fraser are going to be things like the wastewater treatment plants, municipal wastewater treatment plants, industrial wastewater outfalls as well. Pulp and paper mills are known to contain a variety of different endocrine disrupting compounds, but also other industrial sources represent potential discharges to the environment of these kinds of things. Wood preservation facilities, landfills are contaminated sites. So some of these endocrine disruptors are legacy contaminants that we've had around for a long period of time, things like PCBs, dioxins, etc. So contaminated sites and landfills become potential sources as well. And then atmospheric sources. For some of these substances, their fate in the environment is such that they can be released into the environment in the southern, more southern latitudes in the United States, for example, and over periods of evaporation and condensation through summer and winter periods, these contaminants can move northward as well. And things like PCBs and toxaphene and various organochlorine pesticides fall within those groups of things where atmospheric sources are also potentially important.
And atmospheric sources you've mentioned the US, but they could be other places in the world as well that contribute.
Absolutely. Yeah. Other places, for example, where PCBs were not banned until, many years subsequent to when they were banned in North America.
Where on the Fraser system is the majority of the volume of effluent from municipal sewage treatment released?
That'd be the Lower Fraser River Estuary.
Okay. And does
Lower
that,
Fraser and estuary.
does that concentration then of that high volume of effluent have any particular impact on Fraser River salmon in general, or particular stocks? Like, is there some spatial relationship between the volume of release of municipal sewage treatment?
That's an excellent question.
Are you able to answer it with the data you have available to
I
you?
cannot answer that explicitly with the data I have available to me. What I do know is that there may be some differential exposure among stocks, but in terms of actually characterizing what that exposure is for any individual stocks, or even for the Fraser River salmon as a complex, I don't believe we're in a position to be able to do that for most of the substances that are on our list here of endocrine disruptors.
Okay, and what about, where are the majority of the pulp effluents released?
They're released in a variety of locations within the basin. So we have some discharges in the vicinity of Prince George and Kamloops, but also discharges in the Lower Fraser River, some in the Mid Fraser River around Williams Lake as well.
And
so those are the main areas. So it's primarily in the migration routes of salmon is where the pulp mill effluents are primarily.
And the spatial relationship between those releases and salmon in different life cycles, or some particular stocks of the Fraser River sockeye, I take it you have the same answer that you had for municipal sewage effluent?
That's correct.
Okay, we don't have
know
enough.
that there is going to be some exposure. We know that all the stocks migrate through the lower, through the estuary and through the Lower Fraser, and then some of them get differential exposure as they move upstream. But that's largely theoretical rather than being able to characterize exactly what those exposures are for individual stocks right now.
We've talked a lot now about the endocrine disrupting chemicals, but in this chapter you also talk about contaminants of emerging concern. And so first of all, are those two separate concepts, or would endocrine disrupting chemicals also be considered a chemical of emerging concern?
They can, yes. So there can be overlap between those two lists, for sure.
And how do you define or describe contaminants of emerging concern in your report?
Well, that's always a good question about how to define that. There's a variety of different definitions that are out there. I believe I have a definition on one of these pages.
Maybe 105 at the bottom.
Thank you for knowing that. Yeah, 106. So I took this particular definition. I was unable to find a definition, a Canadian-based definition. And so I ended up taking this particular definition from one that had been produced by the Commonwealth of Massachusetts. And so this is not, it's going to be largely consistent with other definitions that have been used either in the Economic Union or other states in the United States. But essentially it included these substances are ones that represent a perceived threat to human health, public safety, or the environment. There are no health standards or guidelines available for them. There's typically insufficient or very limited toxicological data available for evaluating the effects of these substances. And their pathways, sources are relatively new, or there's been some development in analytical chemistry that allows us to understand better what their levels might be in the environment than was possible previously. So if we lower detection limits in the lab, that sometimes identifies emerging problems that we weren't unable to identify previously when detection limits were much higher than what the levels were in the environment.
So the idea of it being emerging doesn't necessarily mean it's a chemical that we've just had introduced into the environment in the last year. They could be chemicals we've known about for a long time, but we don't have sufficient information, as you've identified, to assess them.
Correct.
With that bigger basket of not just endocrine disruptors, but all of these contaminants of emerging concerns, what are the sources of contaminants in the Fraser watershed?
So they have a lot of common sources. So the municipal wastewater treatment plants, the industrial discharges. But in addition to that, for some of the emerging contaminants, we include on that list things like feedlots, for antibiotics that are used in agriculture. That becomes a potential source. Atmospheric sources, we talked about those as well. Wood preservation facilities. Some of the things that have been identified as emerging contaminants also are present in things like anti-fouling paints. It's not like things. It's not that contaminants like tributyl tin or DDTs are emerging contaminants, but that they, in the case of DDTs, we may not have known that they were used in fouling paint in other parts of the world. And those DDTs then find their way into sediments here in North America as a result of shipping traffic that has come from other parts of the world. And likewise, TBT, or tributyl tin, is one of those components of anti-fouling paints that we're starting to understand its effects better. But just starting to understand its effects better, such that we're able to identify what harmful levels are in the environment. And so that's why some of these other things are on the list of contaminants of emerging concern.
On the list of chemicals, the emerging concerns that you've set out on pages 106 to 107, the drugs descriptor there, drugs including prescription drugs and non-prescription drugs, and sex and steroidal hormones, are those primarily found in municipal waste sewage treatment effluent?
Yes, that's correct.
You looked at pesticides in this analysis, I take it?
Yes, I did.
Okay. What data was available to you to locate pesticide use to particular geographic areas in the province?
We relied upon a pesticide sales and use survey that was completed in 2001 by Encon Environmental, and that was summarized in a variety of other places. I think we cited a publication by the name of Viren et al., 2003, as our primary source of that information.
But the sales and survey data, I take it, simply describes that, sales that were made of pesticides. It doesn't locate the pesticide use to any geographic area in the province, is that right?
That's my understanding, yes.
And the other piece of data that you described, Vera or something at all?
They're related, it's the same information.
So that also wouldn't help us determine where in the province pesticides were being applied?
Correct.
Or the volume of concentrations?
It's hard without taking multiple pieces of information and bringing them together. For example, the pesticide sales information would provide a broad perspective on creosote sales within the province. And one could then look at the locations of wood preservation facilities and infer where you might see releases of creosote. In terms of getting numbers for individual facilities, no, you don't get that.
It's not available, is it?
It's not available.
And even on the...
Let me put it another way. If it's available, I was unable to find it.
Okay. And even on the example that you gave, the creosote example, you wouldn't know what concentrations or what time of year or what life stages of salmon were passing through areas that could have that kind of contaminant being released. Is that right?
That's correct.
And certainly for agricultural pesticides, none of that would be tracked in a way that would help us know exactly where they were applied or in what concentrations.
Yes, that's correct.
Okay.
With the caveat that there have been limited number of very specific area pesticide use surveys done in various portions of the province. For the Okanagan, for example, we did one back in 1994 or something like that.
Your company not privately, but your company did that as a
Correct.
Project.
Yes.
There's not a government database that holds
I'm
that
not
information.
aware of a source that would provide that kind of information, no.
All right. Mr. Commissioner, I do have more questions for this witness, so we may want to break now.
All right, thank you. Hearing will now adjourn until 2 p.m.